what this lesson is going to teach us is how to construct a hypothesis test for the difference between two means when you have paired samples, like what we talked about back in chapter 10. Now, if you look at this problem, it says a sample of 8 autos were run to determine their mileage in miles per gallon. Then each car was given a tune-up and run again to measure the mileage a second time. So you've got one group of autos, 1 through 8, and you've got after and you've got before. This is a matched pair designed because you're matching, like if you look at car 7, you're matching car 7's after and before. Now, here's what we found out in this. The sample mean mileage was higher after tune-up, but we would like to determine how strong the evidence is that the population mean mileage is higher after tune-up. And these are paired samples because each value before tune-up is paired with the value from the same car after tune-up. When we have paired samples, the pairs are called matched pairs. By computing the difference between the values in each matched pair, we construct a sample of differences. And if you look at this, what they've done with the after and the befores is they've just subtracted them and they found the differences. And it says if we denote the population mean mileage before tune-up by mu1 and the population mean mileage after tune-up by mu2, then we are interested in the difference. Because these are paired samples, the population mean of the differences, mu of d, is the same as mu of 1 minus mu of 2. Therefore, performing a hypothesis test on mu of d is the same as performing a hypothesis test on the difference of the population means, like what we did in 11.1. Now, here's the notation that we're going to use, just like when we did the confidence intervals for matched pairs. D bar is the sample mean of the differences. S of d is the sampled standard deviation of the differences. And mu of d is the actual population mean difference for the matched pairs. Now, the assumptions are the same old thing. I'm going to do a SRS. And I need to show that my normal condition works by one of the many ways that we've talked about. And you only do this for the difference. All right, and when you look at this, we're not going to go through this. I just left it here in case you need it. This test statistic is the same exact thing that we did before. The only difference is they've got that D bar in place of X bar, and they've got S of D in place of just your S. And then everything else is the same. Now, once you look at this problem, and it says use the data about tune-up improving the car engine gas mileage, test HO, mu of D equals 0 versus H1, mu of D is greater than 0. And I'm using the alpha equals 0.01 significance level. So I've got a very low significance level. Once you've typed in your differences, you're going to go to graph and you're going to do a box plot. And notice that the box plot is fine. It's always going to be fine. And I'm going to sketch it. And I'm going to say no outliers, normal, check. All right, and what your HO is mu of D is 0. That's always what it's going to be. And what your H1 is no, the mean of the differences is greater than 0. All right, so I'm going to go to my calculator. I don't want to do math. I'm going to let the calculator do the math, so I'm going to inference. I'm doing a test. I'm doing a one mean t-test. I'm doing t. My HO is 0. My alternate is greater than 0. So change that to greater than 0. I'm going to use a data set. That's going to bring in my data. And my significance level is 0.01. I'm going to go to next. And I get my test statistic, which I need, and my p-value below. Here's going to be what I'm going to write out. I'm going to do a one sample t-test. And I need my test statistic, t. is 9.143. And I'm going to go up here, write your number out, 1.925. I've got some more digits and I've got e negative 5. You need to move the decimal 5 places to the left, which means you need to add 4 zeros. So I'm going to do 0.0001925. All right, and just double check yourself. 1, 2, 3, 4, 5. Here's what I would say for my p-value. If you round that to 4 decimal places, you could say approximately 0. I'm going to say on this one, I'm going to say 0.0, 4 zeros and a 19. If you had an E with more than 5, you would definitely just say approximately 0. All right, so here's what I'm going to say. Now, my p-value is very low, and my HO is going to go. All right, so I'm going to say, since my p-value of 0.040 is less than alpha equals 0.01, we will reject HO. We have enough evidence to conclude the true mean difference is greater than 0. And what that means is gas mileage improved. You would not have to put that, but gas mileage improved. And for my interpret, I'm going to say if HO is true, there is a 0.040 chance of a test statistic as extreme or more extreme than ours. And ours is T equals 9.143. For the next thing, we're not going to do this problem, but I just want to set it up. And it says, following are the annual amounts in rainfall in inches in 6 randomly chosen cities for 2 consecutive years. Can you conclude that the mean rainfall was greater in year 2 than in year 1? Okay, so I want to know if it's greater in year 2 than in year 1. All right, so here's what I'm going to do. And like I said, we're not going to do the whole thing. I just want to set up our HO and our H1. Sometimes I think the H1s are hard on Alex. All right, so here's what I want to know. HO is always mu of D is 0, okay? Now, H1, it says, can you conclude that the mean fall was greater in year 2 than in year 1? Okay, so I want to know, is year 2 greater than year 1? And I can't write it like that, year 2 greater than year 1. I need to do something about these differences. And what you want to do with these differences is you either want to say not equal to 0, greater than 0, or less than 0. And here's what you're going to do. Pick one pair where the rainfall was greater in year 2. Okay, so like I'm going to pick this first one. You could pick any one where the rainfall was greater in year 2. And I'm going to actually subtract them. And I'm going to get 34.6 minus 25.1. And I get 9.5. Okay, now, I get a positive number because the rainfall was greater in year 2. If you went down the chart, every time it was greater in year 2, you got a positive number. So can you conclude that the mean is greater in year 2? I want to say mu of D is greater than 0. And like I said, that's because that 9.5 is a positive number. Once you've entered your once you've got your differences, check them with mine, enter them in the calculator, just the differences. Once you've done that, turn the video back on. Our conditions are going to be SRS. I'm going to go to my statistics. I've entered my data. I'm going to graph it, box plot. There's my box plot. No outliers. Normal check. Now, when you do your HO and your H1, it says for H1, can you conclude that the mean time for the rear brake pads to wear out is longer than the mean time for the front pads? Okay, so look for one of your answers where the rear was longer than the front. Okay, I don't have to look far because it looks like they're all like that. So here, I'm going to look at first one. Rear was longer than the front. 9.9 is positive, so that's going to be greater than 0. If 9.9 had been negative, I would have said less than 0 if that had been the case. All right, so I'm going to do for H1, mu of D is greater than 0. HO, mu of D is 0. Mu of D is greater than 0 because the rear is more. When you subtract it, it's going to be positive. And like I said, you got to think about that sometimes. I'm going to go to my inference. I'm going to do a test. I'm going to do one mean, t-test. My null is 0. My alternate is greater than 0. And I'm going to pull in my data set. And it's a 0.05 level. Now, look at your test statistic, how far out that is. All right, so here is my answer. I did a one sample t-test. My t is 60.277. And my p-value is very small. E negative 12, you'd have to move the decimal 12 places. You'd have to add 11 zeros. So here's what I'm going to say for P. You could say it equals 0. I don't like to say it's exactly equal to 0, so I'm going to say it's approximately 0. But if you said equal, it would be fine. P-value is very low. HO is going to go. All right, so I'm going to say, since my p-value of approximately 0 is less than alpha equals 0.05, we will reject HO. HO is gone. We have enough evidence to conclude the true mean time for the rear brake pads to wear out is longer than the front. The true mean time for rear brake pads to wear out is longer than the front. And lastly, I'm going to say, for my p-value, I'm going to say if HO is true, there is a approximately 0% chance of a test statistic as extreme or more extreme than ours. And ours is t equals 60.277.